Hello and welcome to this Realist Simulation What's New presentation for our first release of 2023. My name is Charles Teconose. I am the product manager responsible for Realist Fluids 3D Computational Fluid Dynamics Suite, Vectis. Over the next 20 minutes or so, I would like to give you an overview of some of the new and exciting features in this 2023.1 release. Our fluid product, Vectis, is a detailed 3D CFD and solid heat transfer tool for propulsion and thermal systems. In this presentation, I will talk about the objective and directions we are taking with Vectis, as well as how these are mapped into the offering we deliver in this release. We will then go through the key features of 2023.1 and discuss how these answer the CA challenges our customers are facing and help them build better product, faster, and more cost efficiently. The aim of Realist 3D Fluids offering is to deliver expert 3D CFD capability for your engineering solutions. As a provider of expert 3D CFD, our team specializes on providing bespoke and tailored solutions, helping our customers address complex problems in combustion and thermal analysis. This is enabled by our state-of-the-art IC modeling capability and efficient coupled thermal analysis solver. The design and development of our 3D CFD product is informed by the engineering expertise of our business, embedded in software workflows. Finally, 3D Fluids products are seamlessly integrated in the wider Realist ecosystem, including tools for system simulations, 1D fluids, and mechanical analysis. The 2023.1 release focuses on helping our customers address the challenges engine developers are currently facing, namely the drive to develop even more optimized powertrains with low emission, while reducing the cost of the development process. Thus, in this release, we bring new features that increase Vectis' predictive capability, while also improving the workflow and user experience items in a drive to allow our customers to save on their most valuable commodity, engineer's time. To this end, we have introduced new models aimed at the development of complex gasoline or hybrid fuels and green hydrogen combustion, with new spray analysis option, a decoupled knock model, and further enhancements to our unique hydrogen combustion modeling capability. A new automation approach of the CAD to mesh process is introduced, thus allowing to script the whole simulation process from CAD to computation through a single Python script. This allows our customers to build simple yet efficient workflows for complex analysis and integrate Vectis into design of experiment or optimization loops. A new feature is also introduced in our post that allows to bulk post-process results from parametric analysis very efficiently. Additional improvements are also brought for our pre- and post-processing tools with, amongst others, a revised interface in our geometry. Let us now dive into some of these features and consider what the simulation challenges are, what are the solutions we provide, and how our users can access these solutions. Accurate modeling of hydrogen combustion unlocks the potential for the optimization and design of carbon-free powertrains. In this release, we have extended the range of turbulent flame speed models applicable to hydrogen combustion by adding a modified power law version. This addition is fully compatible with our newly released state-of-the-art laminar flame speed modeling, accounting for the special thermodiffusive character of hydrogen flames. The model is easy to set up and its calibration is similar to its standard counterpart, while allowing for an increased accuracy over a large range of operating conditions met in hydrogen fuel engines. The animation here illustrates the injection of gaseous hydrogen in a single-cylinder research engine at Ricardo, whose investigation formed the basis of a joint Realist-Ricardo publication presented at the SA World Congress in April 2023. A comparison of our new model against DNS data obtained in collaboration with Newcastle University is shown here, where each point represents a different set of thermochemical and turbulent conditions. This plot illustrates the excellent predictive nature of our new formulation compared to DNS data. The pressure and heat release traces obtained with Vectis on the Ricardo single-cylinder hydrogen engine are shown here for different operating points of a lambda sweep from lambda equal 2.5 to lambda equal 3.5 and compared with experimental measurements. The calibration is done for the lambda equal 3 point, and the new model is shown here in the blue curve while the older formulation is shown in red. And it can be seen that the new formulation improves considerably the agreement with the experimental results compared to the standard formulation. This is particularly the case for richer but also for leaner conditions. Finally, we can look at some key metrics of the combustion, such as pressure peak magnitude, pressure peak timing, 10 and 15% burn, where it can also be seen that the new formulation improves the prediction consistently. This highlights the key strength of the new approach in capturing the changing influence of the thermodiffusive instability across a range of conditions, leading to a much more robust and accurate prediction. Now more than ever, we need refinement and optimization of gasoline powertrains to lower emissions and improve performance. Part of the answer lies in the in-depth understanding of fuel injection and mixing, both of which are driven by the liquid spray behavior. This understanding then leads the development and optimization of new advanced fuel injection system. Vectis now provides additional advanced spray analysis options to enable advanced measurements, allowing for direct comparison with experimentally measured metrics. These options include the injector half angle, penetration along a given user-defined axis, and not only along the various holes directions, etc. In particular, this allows to capture spray collapse accurately. It is accessed through a simple new tab in the injector panel, shown here, where the user has various options available. A representative 6-hole injector using a GDI engine is shown here, where it can be seen that the actual penetration is fairly different from the penetration of the individual plumes. The angle of the injector, shown here between the droplets, also varies quite significantly in time. These statistics are captured accurately using our post-processing options, as shown here with the penetration as a function of time of the individual plumes and the penetration along the user-defined actual direction. The half angle of the injector is also shown here as a function of time. The automation of complex workflows can save time, but can also help avoiding user errors which can lead to delays in simulations. In this release, we are introducing a new fully scripted CAD to mesh workflow. It is enabled by command logging and batch processing in our geometry pre-processing solution. The features is accessed through a fully documented command interface, and there is a new pre-processing tutorial demonstrating the CAD to mesh workflow automation. Furthermore, our geometry in 23.1 features a new improved tabbed interface and can support IC pre-processing for geometries which are exported from CAD as a single fluid volume as opposed to separate solid parts. This is also illustrated in the tutorials. The full mesh preparation workflow starts with defining the color table for mapping CAD colors to boundaries. Then proceed with the import of the CAD, the motion definition, the zone definition, and the generation of the simulation DOM. We then move on to the generation of the surface mesh for the domain and the moving parts, and then the definition of the volume mesh. Finally, we can define boundary and volume refinement before the generation of the volume mesh. The color table is imported in Excel format, defining each boundary by RGB components and name. This color table is set in RDesk preferences for our geometry, as shown here. Similarly, the log file name for command logging is set in RDesk preferences. When we import CAD from any format supporting colors, such as STEP for example, the boundaries are recognized based on the provided color table and are automatically created in the session. The commands covering what we do interactively in the GUI appear in the log and can be reused. With this functionality, here's how simple the full workflow becomes. The script here creates a new RDesk session, defines the color table, and then goes through all the steps of meshing in a simple to follow scripting language. The script can then be executed from the command line with or without GUI. When we run this script, the geometry is first imported, the colors are automatically mapped to boundaries, the background geometry is generated, and the surface mesh is defined and created. The volume mesh is then defined and created in minutes as well, as we can see here with the refinement box. This fully automated process takes us from CAD to mesh in just a few minutes. And we can then inspect the resulting mesh using our viewer. The ability to efficiently post-process a large number of simulations from a DOE or a parametric sweep increases the efficiency of the CAE process by allowing to spend more time analyzing the key results extracted. In this release, we are enabling such fast extraction by introducing a mechanism to bulk post-process simulation results. When a parametric sweep is done in Vectis, our post now has the ability to load and plot the data of multiple cases with just a few clicks. It also has the ability to cross-plot results between the different cases, to easily compare and extract the most of the simulation data. Furthermore, it is easy to define a small subset of cases to investigate a particular region of the parametric space. An example of using this feature is provided in an extension of the Catalyst tutorial in the Vectis manual. I will also demonstrate briefly this feature in the case of a simple intercooler, as shown here, where the inlet temperature and inlet velocity of the water are varied in a sweep before analyzing the results. We start from the Vectis session, where a parameter is defined for the water temperature with a default value of 350 Kelvin. A parameter is defined for the water velocity with a default value of 0.1 meter per second. The case table is now accessed, and a parametric sweep is defined as a function of two variables, the first one being the water temperature, varying between 325 Kelvin to 375 Kelvin by step of 25 Kelvin, and the second parameter is the water velocity, with values of 5 centimeters per second, 10 centimeters per second, and 15 centimeters per second. We now have defined 9 cases in our sweep, and we can generate the 9 input files. You will note that an additional case header file has been created, and it will be used to load the data in Upload. Our post session is now open, and we can load the repage or header report file. The individual cases are available, and we can plot, in this case, the temperature at the outlet of the intercooler for the water in the 9 different cases in just a few clicks. We can now also compare the same variable, the outflow temperature, between the different cases, and we select the last value from the calculation instead of the mean. And we can see here that the temperature is now plotted as a function of the cases. Using the custom plot creator, we can now create a contour map of the outflow temperature as a function of both input parameters. This map then shows the results of the simulation and linearly interpolates the results in the available range. Finally, the last type of custom plot available uses a single variable as the x-axis and puts the other variable as various curves. In this case, we've chosen the water temperature as the input variable, and then 3 curves are obtained for each value of the inlet velocity. Other notable features of this release are designed to help our customers transfer and enhance their existing Vectis workflows and take full advantage of the new solver technology, as well as improve their experience. We have the inert knocking model that allows for more efficient knock calibration, an increased range of ethanol-gasoline blends available in the material database, the ability to export molar fraction for RTZF and CPV species to simplify the direct comparison with experimental data. Various enhancements in the GUI extend the range of data being parameterized, such as moving surfaces, file names, etc., to enable more complex parametric analysis and geometry optimization. The aerodynamic moments can now be exported for every wall surfaces, and an improvement of the GUI allows the automatic selection and deselection of equations to improve the user experience and reduce the number of errors. vPre has been modified to deal with a very large CGNS grade conversion to Vectis format. And finally, various improvements have been brought to RViewer for PDF extraction and speed of plotting isovolume and isosurfaces. As mentioned before, a revised interface has been delivered for our geometry with a tabbed and ribbon-like feel. Finally, a number of new and improved training material allow our users to take full advantage of the new features and adopt them in their workflows. For example, we have added materials detailing the import of grid generated with ENSA or the coupling of VSolve and GT in co-simulations. This takes me to the end of the talk, where a highlight of the most important features of previous releases is detailed. In the past year or so, we have brought a new combustion workflow aimed at robustly and accurately predicting the effects of fuel composition on the emissions of engines by a coupling between the tabulated and on-the-fly detailed kinetic frameworks. This introduced new advances such as a new suit model, various speed improvements for both the tabulated or the on-the-fly detailed kinetic computations. This new approach aims at facilitating the adoption of new legislation requirements for classical combustion engines powered by drop-in or e-fuels. We have also added a new decoupled knock model aimed at premixed or partially premixed application, relying on the CPVG equation framework. An additional feature was brought to improve the simulation of piston cooling by using the volume of fluid method to simulate the fluid and liquid motion in the piston gallery or under the crown. This simulation results can be coupled with Realis phase or Vulkan softwares to provide more accurate heat transfer predictions. We also delivered a large speedup of the GUI that allows to deal efficiently with very complex cases such as underhood or CHT simulations of complete engine blocks. Then, we geared towards better usability by introducing a new tool, geometry, aimed at replacing the previous pre-processing suite. This new tool supports the whole process from CAD import to mesh export. It is capable of generating high-quality, watertight surface meshes and provide numerous tools for CAD and mesh manipulation. It helps in reducing even further the turnaround time between CAD and mesh, while still maintaining quality. Finally, in a drive towards saving engineers' time through scripted workflows, we introduced various new features enabling the generation of parameter sweeps or DOE with just a few clicks in a single Vectis session. This helped reduce considerably the time required to explore large design spaces. Vectis workflow automation was also enabled through a new Python scripting capability, a few examples of which are provided in the training materials in the manual. With the introduction of the CAD to mesh scripting, presented previously, the whole CAD to result process can now be controlled through a single Python script. In summary, we are continuously trying to match the most pressing engine challenges to make Vectis the world's best CFD toolchain for powertrains. Thank you for your attention. If you'd like to find out more, please visit www.realis-simulation.com or contact us at support@realis-simulation.com.